Alright, in this tutorial right here, I'm going to introduce to you what logarithms are and some properties of logarithms you might want to write down. Alright, so what are logarithms? So imagine this. Imagine you have an exponential function, right? Where you have e to the x, or 2 to some value x, or 2 to the fourth. Those are exponentials, right? Where some number is being raised to another. So the logarithm is basically the exact opposite. So you have the function e to the x. So what corresponds to e to the x would be the natural log. So natural log has a base of e, right? So when you have 2 to the x, you're going to have some logarithm form. And the logarithmic form is capitalized log, or just log, right? So a log, and I'll show you graphically what these are intuitively. So when you have an exponential function, right, it goes like this. It curves up and it grows rapidly, right? So logarithmic function, what it does is it starts out with a curve, but then it flattens out kind of like that over time. Alright, so that's if you want to see them graphically. Alright, so a log, if it has no base, a log is assumed to have a base of 10. Alright? A natural log, ln, has a base of e. Because a natural log is a log with an exponential base. Alright? So, I'm going to give you a couple other formulas to prove this. Alright, so, a couple of properties of logarithms we're going to write down real quick is when you have log base, let's say you have log base a raised to the b is equal to c. So that's a logarithmic form, a generic formula, right? So what I'm going to do is I'm going to convert this to exponential form. And I'm going to do this by moving the b and the c around on each side of the equation. So what I'm going to do is I'm going to write the a, and it's going to be the base a, right? And it's going to be raised to the c is equal to b. So what I do is I get rid of the log and convert it to exponential form. So that's the property of logarithms we're going to need to know, and I'm going to apply it in this video. Alright, how about this property of logarithms? So let's say that you have log a plus log b. Alright, log a plus log b is going to be log, and then inside the parentheses, a times b. Alright, and then assume that you have log a minus log b. It's going to be log a over b. And it corresponds, if you could think about like the exponent rules and all that. So you have a negative log, it's going to be on the bottom. If it's going to be a positive log, it's going to be on top when associated with this property of logarithms. Another property of logarithms is I'm going to write is assume you have log base x raised to the n. Alright, so when you do algebraic problems associated with logs, which I'll do eventually, what you're going to do here is going to move the n, which is the log is being raised to n, right? And you're going to move it in front of the log. So it's going to be n log x. And that's a couple of property of logarithms I want to introduce to you in this video. And I'll do other videos, and I'll do examples in this video right here, showing you in a couple of these examples. Alrighty, convert the following to exponential form. Alright, so the formula we're going to use for this is going to be log base a to the b is equal to c. And to convert this to exponential form, what I'm going to do is I'm going to move the b and the c around. And I'm going to get rid of the log. So a to the c is equal to b. Alright, so what I'm going to do is I'm going to quickly apply it to these problems. So I have log base 4 of 1 over 64 is equal to negative 3. So what I'm going to do is I'm going to quickly identify what a, b, and c are. So a, the base of 64, or 4. B is going to be 1 over 64, and then C is going to be negative 3. So I'm going to do is I'm going to just move around the 3, negative 3, and 1 over 64 and get rid of the log. So 4 to negative 3 is equal to 1 over 64. Alright, try this one. Log base 128 raised to the second power is equal to 1 over 7. Alright, so what I'm going to do is I'm going to quickly identify the base A, B is 2, and then C is going to be 1 over 7. Alright, so what I'm going to do is I'm going to just move these around on each side of the equation. So it's going to be 128 raised to 1 over 7 is equal to 2. Alright, convert the following to logarithmic form. 3 to the 4th power is equal to 81. So what I'm going to do is I'm going to do exactly the opposite of what I did when I converted these to the exponential form, using the same formula. So what I'm going to do is I'm going to write out log. Alright, so the base is 3. That's the A. 4 is actually going to be the C, and then the B is going to be 81. And the reason why is because I keep the base 3, right? So what we're going to do is we're going to move the B and the c around, just like what we did. So it's going to be 3 to the 81 is equal to 4. And that's how I can convert it to logarithmic. So we have the a, b, and c just like this form, like we had in these other examples. Alright, try this one. 64 to the 1 over 6 is equal to 2. Convert this to logarithmic form. So what I'm going to do here is I'm going to write out log, alright? So 64 is the base, which is a, right? What I'm going to do then is I'm going to have the c, which is 1 over 6, and a b, which is 2, alright? So what I'm going to do is I'm going to move these around each side of the equation. So 64, log base 64 of 2 is equal to 1 over 6. Alright, consider these problems. Alright, so we have log base 2 raised to 64. Alright, so when you see a problem like this where it's asking us to find some c value, or find some output value of this, what we're going to do here when we have a logarithm, because they're interchangeable exponents, right? They're the exact opposite. So an exponential function grows rapidly. A logarithmic function grows, but slowly. It starts curving and it starts flattening out eventually. Alright, so what I'm going to do here is I'm going to ask myself, well, 2 to what power is equal to 64? Alright? So it turns out that 2 to the 6th power is equal to 64. And I can prove it when I write in its exponential form. So if I move these two numbers around on each side of the equation, if I get 2 to the 6th power is equal to 64 then. Alright, so that is true. Alright, how about this one? Log base 3 of 81. So 3 to the what power is equal to 81? Well, it turns out 3 to the 4th power is equal to 81, so the output value is going to be 4. Alright, how about this one? Log base 5 of 25. So, 5 to what power is equal to 25? It turns out the 5 to the squared, or 5 to the 2nd power, is equal to 25. Alright, try this one. Log base 4 of 1 over 64. Alright, so it's asking us, well, 4 to what power is equal to 1 over 64? So, we know that 4 to the 3rd power, or 4 cubed, is 64, right? But notice how we have a fraction here. It's 1 over 64. That's right. Alright, so what I'm going to do here is, since there's a fraction right here, this is going to be negative 3. Because 4 to the 64th power, or log base 4 of 64 will be 3. But since it's 1 over 64, it will be negative 3. Because the fraction makes it negative. If that makes sense to you. Alright, how about this one? Log base 25 of 1 over 5. Alright, so 25 to what power is equal to 5? Alright, it turns out that 25 to the half power, the square root of 25 is 5, right? Since it's negative 1 over, or since it's 1 over 5, it's going to be negative 1 half. Alright, how about this one? Log base 1,000. So using the property logs where we have log base 10 is a generic logarithm, right? With no other base. What I'm going to do here is I'm going to count the amount of zeros I have. So 1, 2, 3, I have 3 zeros. Because log base 10 is 1, right? Log base 100 is 2. Log base 1,000 would be 3. And log base, like, let's say you have log base 10,000 would be 4. And the reason why they are what they are is because you can count the zeros. So log base 10 has 1. Log base 100 has 2 zeros. Log base 1,000 has 3. So log base 1,000 will be 3. And you can think about it like that, though, when you see problems like these.